Next to the sun, the moon is the brightest celestial object in Earth's sky, and what a beautiful sight it is. We take it so for granted. The moon is essential for advanced life on Earth, which we don't really think of, and that's not the purpose of this segment, which is really to just look at the phases of the moon and understand them, and also to consider how much of the moon we can actually see as the moon orbits the Earth. Here's a high-resolution picture of the moon. It's great to look at the moon when it's not full because the sun is at a glancing angle where you can see the details of the craters, so that's pretty awesome. If you ever see a photograph like this, you can be assured that it's false. Now the idea is that this is taken from the North Pole, and that's why the moon looks so incredibly massive up there in the sky. Well, it turns out that if you take the trek to the North Pole, as awesome as that might be, you're not going to get closer to the moon. And even if you got a whole Earth circumference closer to the moon, it wouldn't change appreciably the size of the moon compared to the sun. In fact, both the sun and the moon subtend about a half-degree angle in the sky. And of course, this is far exceeding the angular expanse of the sun. So we know for sure that this is a false image. Well, let's discuss the phases of the moon, and it's really not so hard to understand. We have sunlight beaming in on the Earth, and notice every image here as the moon progresses around the Earth, you'll notice how much of the moon is lit up. That's right, it's 1/2. Half of the moon is lit all the time, and of course, it's the half that's facing the sun. Well, that's always the case, and yet, from an Earth point of view, we don't always see all that lit up side. In fact, the only time we see that is during the full moon over here. During the new moon, we see only the side that's not lit up. So because of the Earth point of view, we have what's called the phases. So here's the phases as seen from Earth. So starting with the new moon, and keep in mind, here's the Earth spinning around. We're looking at it from above the North Pole. Okay, so that's the view. The new moon, we don't see any of it. That's over here, because the side that's lit up is directly away from us. The waxing crescent, waxing means increasing, and it's just the crescent over here on the right-hand side. You see on the right-hand side, we see the part of the moon that's lit up. A quarter way around its orbit, it's at first quarter. Makes sense. And we see the right-hand side lit up from the point of view of Earth. There it is, first quarter. And then waxing still, increasing, waxing gibbous. We see most of the right-hand side of the moon lit. There it is. Just the sliver on the left-hand side that's not lit. Then full moon. So we see it completely lit. Progressing around, we have kind of the waxing sequence in reverse. We have the waning gibbous. Now it's the left-hand side that we see most of. The right-hand side has a sliver that's not lit. The left-hand side is all lit. Third quarter, half of it's lit on the left-hand side. Waning crescent, the only thing that's lit is a little bit on the left-hand side. And that's the full sweep of the phases for the moon. And here is the 24-hour equivalent to noon, sunset, midnight, and sunrise. Well, what about the amount of the moon that we see? Do we see the entire moon? As the moon goes around the Earth, it turns out that, as seen by this little spiky point on the moon, which is fixed to the moon, we see the moon directly faces us all the time. That's really peculiar. Really peculiar. So if a question was asked, does the moon rotate? How would you answer that? Well, if it didn't rotate at all, then you could imagine this spiky point pointing to the left. It would stay pointing to the left. And over here would be pointing the opposite way it is, be pointing this way toward the left, if it wasn't rotating at all. In order for the moon to always have the same face pointed to us, which of course is the face where the man in the moon lives, The only way for that to happen is for the moon to actually rotate ever so slightly, so that when it makes one complete revolutionary orbit, it is rotate around precisely once. That's the only possible way, logically, that the moon can face the Earth at all times. So that's fairly amazing, and I'd like to explain that just a little bit. First, realizing, though, that the Earth and Moon, to scale, are much further away than you see here. Here's the Earth, here's the Moon to scale. So when we discuss eclipses, you can imagine one of the questions you might have had all along here is, well, here's the sunlight coming in, and the Earth being here is pretty big, and wouldn't it block the light to the moon? You see it all lit up here. How can that be? Why isn't the Earth in the way? Well, one way to make some sense of that is seeing just how far away they are, and the shadow of Earth could easily miss the moon, and we'll discuss that more in the next segment. But in any case, how is it that the moon faces the Earth all the time? Well, it's easier to demonstrate this with other visuals, I suppose, but I'll try and do it verbally just briefly. And that is as follows. The Earth, through its gravity, tugs on the moon. The Earth's tug on the near side of the moon is greater than on the far side of the moon. Therefore, since it pulls harder on the near side than the far side, it elongates the moon. The moon is slightly egg-shaped. Now, if the rotation rate of the moon were any different than what it was, say it's a little faster, this elongated shape would actually be more oriented like this then. You can see there's a bulge over here, and the Earth would pull harder on that bulge and try to rotate through torque the moon back into alignment. If the moon were rotating slightly slower, then the bulge would have a tendency to be preceding the alignment between the Earth and the moon, and the Earth's tug on the bulge would take precedence, and it would drag or put a torque on to speed up the rotation, so once again it's lined up. So any differential rotation of the moon, other than one rotation per revolutionary period, any differential from that, the Earth is going to apply a torque to the resulting bulge from the tidal effect, from this harder pull on one side than the other, and it's going to try and force the moon to line up so that it's always facing one side. So it always has one side facing us. Now this takes billions of years to fully take place, but that's what's happened over the approximately 4 billion years that the moon has been in orbit around the Earth. So we always see one side of the moon. The Earth stretches and twists the moon to align it. So we have what's called tidal lock. The moon being locked to the Earth is called tidal lock. It's the same effect as the tides that we are familiar with water. And finally, just to mention, there is no dark side of the moon. So that's explicable from the standpoint that, as we've already seen, if we have the same side facing us, then at some point in its orbit around, the sun is going to shine on all parts of the moon. Not all at once, but progressively. All parts of the moon are going to be lit up. For instance, over here, would be a new moon, and you see the far side of the moon, the side that we don't see, is fully lit. So it's not dark. So there is no dark side of the moon, but there is a far side. The far side is a consequence of this tidal lock. We never see the far side, but the far side is lit up. So there you have it. To visualize the moon going through its phases very rapidly, here is a succession of images showing exactly that. And there's some little complexities, as you can see, some wobbling and jostling around. And part of that is because the moon is not in a perfectly circular orbit. It is slightly elliptical as it goes around the Earth. To better understand what the moon looks like at different times and its different phases, this shows half of the sequence of the moon's phases. And in this sequence, we are looking at the evening sky. We show here the sun setting in the west. So this is sunset, and it's sunset for all these images. So we're looking at new moon through first quarter to full moon. Well, new moon just simply means that the moon is in line with the sun, and so you don't see it at all. And then each subsequent day, you have various increasing amounts of crescent until the first week transpires and you have the first quarter after the first week. So that's a waxing crescent. And notice that at that time when the sun sets, the first quarter is directly south. Then in the next week we have an ongoing increasing amount of the moon being shown. So we're in the waxing gibbous phase as we go to day 14, and at approximately day 14 at least, we have the full moon. Well, where's the full moon? It's on the exact opposite side of the sun. So the sun is setting and the moon is rising in the east, basically 180 degrees away from the sun. So it's looking in the other direction of the sun, and therefore the moon is shown in its full phase. So that's the first 2 weeks, and now we'll take a look at the other side of the story. This really picks it up where we left off on the previous discussion, but we now have the sun rising in the east. Well, in the last image we had the full moon rising in the east, the sun setting in the west. 12 hours later, the sun is rising and the moon is setting in the west. So this is the morning sky, all these images, and when we have the full moon here, the subsequent motion of the moon around the earth causes it to misalign with the sun, the earth, and the moon. That alignment is no longer perfect anymore, and we start waning. And so the first week, or actually it's the third week of the sequence, we have a waning gibbous phase to third quarter, and then in the final week, as the moon continues to progress around the earth, it's approaching alignment with the sun again, waning crescent up to the new moon, and that completes the entire cycle. Well, in the last part of this segment, I want to consider the time it takes for the moon to orbit Earth. And that may not be as simple as you might think at first, because while the moon is orbiting the Earth is also orbiting the sun. So in our perspective here, we have a new moon. Here's the sun, moon, and Earth. They're all lined up. So from the Earth point of view, we see a new moon. We don't see any of the moon. It's all lit on the other side. So, what is one orbit of the moon? Well, we would normally think of it as the time that it takes to see a new moon again. We want to see a new moon again, and then we think, the moon has orbited the Earth exactly one time. But not so. And that probably isn't surprising to you because we already discussed sidereal and solar days. The solar day is where the sun looks the same again. It's crossing the meridian at high noon from the previous day, and yet we discover that the Earth has rotated more than once. It's once plus about a degree. Well, the same consideration holds here. So here's the moon making one complete orbit around the Earth, 360 degrees. During that interval of time, the Earth has moved about 30 degrees in its progression around the sun. So if we look at this line, it's lined up with the sun and the background stars back here. Well, when the moon makes one orbit, it's once again aligned up with the background stars, but not with the sun. So look at the moon here. Does it look like a new moon? I don't think so. The moon has got to go this extra arc, an extra 30 degrees, in order for it to be lined up with the sun again. So it has to orbit more than once. Now the actual orbit of the moon around the Earth takes 27.3 days. But it hasn't gotten there yet. It hasn't gotten to the place where it looks the same, where it's a new moon again. So that's a problem. We need to have that extra 30 degrees of orbit before it has the same phase again. So that's the key. How long does it take to orbit that extra 30 degrees? 2.2 days, just about exactly. So the entire time it takes to see the same phase is the 27.3 plus 2.2 is 29.5 days. And that's what we mean by a synodic month. The time it takes the moon to appear to be in the same place, to have the same phase that it did the last time we saw it in the new moon or full moon or any other phase. Phase to phase, 29.5 days. One orbit plus about 30 extra degrees. Hopefully that makes sense. We'll see you in the next presentation.